Welcome, everyone. Step right through these double doors with me and into our state-of-the-art civil engineering laboratory. Just look at this place. The steel benches are completely spotless, the air is perfectly still, and today we're taking you on a really immersive tour of the ultimate cement testing lab. We're going to break down all the essential tests of cement that you'll see popping up constantly in state examinations. By the time we finish up this tour, you'll have a total grasp on the purpose, the apparatus, the procedure, and those absolutely critical exam points for each and every test. Okay, so let's dive right into this. You know, before a single brick is laid down or a single foundational beam is ever poured, civil engineers face a pretty massive responsibility. Cement is, without a doubt, our most important construction material. If the cement is flawed, well, the entire structure is literally at risk. And that's exactly why we have to verify its structural integrity through these really rigorous physical and chemical procedures. The stakes are incredibly high out there in the field, and the margins for error are razor thin. We have to be 100% sure the material possesses the exact strength, durability, and quality required before construction even gets a green light. So here's our laboratory manifest for the day. We've got 5 stations to hit. First up is fineness and consistency, then setting time tests, followed by soundness and compressive strength, the specific gravity test, and we'll wrap it all up with an essential exam review. Let's get moving. All right, Station 1, fineness and consistency. Let's step up to this first bench and take a look at exactly how particle size and standard paste requirements are measured. We're starting things off with the Fineness Test. The whole objective here is simple, but totally vital, and that's determining the particle size of our cement. Why? Because finer particles mean a much faster rate of hydration, which directly leads to better strength development. To actually test this, we take exactly 100 grams of cement and place it onto a highly precise 90-micron sieve. We shake that sieve continuously, and then calculate the exact percentage of cement that gets retained right there on the mesh. Take a look at the high-definition precision of the tools we're using here. We've got the 90-micron sieve, a highly calibrated weighing machine, and that mechanical sieve shaker. But here is the absolute most crucial point for your competitive exams, so definitely take note. The residue retained on that sieve must never, ever exceed the specified limit. You'll definitely want to etch that into your memory right now. Moving just across the bench, we transition into the standard consistency test. Our goal here is to find the exact quantity of water needed for a standard cement paste. To do this, we prep a paste and place it right into the VCAT mold. Then, we let this metallic plunger penetrate the sample. As it drops, we're carefully recording the exact amount of water required to achieve the correct depth. So the really critical point is knowing exactly what that quote-unquote correct penetration actually looks like. The plunger has to penetrate to a distance of exactly 5 to 7 millimeters from the bottom of the mold. It requires some incredible precision, and visualizing that tiny 5 to 7 millimeter gap in your head is going to serve you so well, both in practical lab work and on your exams. Let's move on to Station 2, setting time tests. We're keeping our VCAT apparatus set up right here, but we're shifting our focus to those crucial windows of plasticity and hardening. This setup brilliantly illustrates the difference between our 2 main timing tests. For the initial setting time test, we want to pinpoint the exact time it takes for the cement to just begin losing its plasticity. We use the VCAT apparatus, prep the paste, fill the mold, start up our stopwatch, and let the needle penetrate at regular intervals. We stop the clock the moment that penetration becomes insufficient. Now, on the flip side, the final setting time test determines the time required for complete hardening. We're still using the VCAT apparatus, but this time we keep measuring until that needle no longer leaves any impression whatsoever on the surface. Now let's talk about the hard numbers. 30. 30 minutes is the absolute minimum initial setting time. This is a completely non-negotiable metric. The cement has to remain plastic for at least this long just to be workable on a busy construction site. And then on the other end of the spectrum, we have 600. The maximum final setting time should never exceed 600 minutes. Think about it. If it takes longer than that to harden, your entire structural timeline gets completely compromised. So 30 minutes minimum, 600 minutes maximum. Make sure you lock those 2 numbers in. All right, let's head over to Station 3, soundness and compressive strength. We're moving into the heavy-duty section of our clean lab environment to focus on post-hardening volume and sheer physical load. First up in this heavy-duty section is the Soundness Test. The main objective here is to figure out the ability of the cement to actually retain its volume after it has hardened. For this, we're using what's called the Le Chatelier apparatus. We prepare our paste, fill up the mold, and then immerse the whole sample in water so we can accurately measure its expansion. Now, why does this even matter? Well, this test is incredibly important for detecting excessive quantities of free lime and magnesium oxide. Those specific compounds can cause catastrophic volume changes down the line and seriously compromise the long-term durability of a structure. Next up, we arrive at what is arguably one of the most exciting and critical tests of all, the compressive strength test. To find out just how much force our cement can actually handle, we prepare mortar cubes in a very specific cube mold. We cure those cubes in water, then we place them right into this massive compression testing machine. Just imagine the slow, intense, immense hydraulic pressure being gradually applied to that cube. More and more weight presses down until, finally, failure occurs and the cube just shatters. That exact breaking point, that is our compressive strength. For this particular test, precision is quite literally everything. 70.6 represents the standard cube size in millimeters. That's a 70.6 millimeter cube mold. This is yet another really vital anchor point that you are absolutely going to see again on your exams, I guarantee it. Let's move smoothly over to Station 4, the specific gravity test. We're stepping under some bright cinematic lighting here to look at one last vital chemical property. The objective at this station is to determine the specific gravity of our cement. Take a really close look at the elegant glassware on the bench here. This is the Le Chatelier flask. Now, be careful, do not confuse this with the Le Chatelier apparatus we used just a few moments ago for the Soundness Test. They are different. This specific flask is designed explicitly for calculating specific gravity. And the magic number you absolutely need to remember here is 3.15. The specific gravity of ordinary Portland cement generally sits right around 3.15. Go ahead and lock that exact decimal point right into your memory bank. All right, we've made it to Station 5, Essential Exam Review. Synthesizing all of this data we just gathered is the ultimate key to solving those tricky exam questions in just seconds. Let's quickly align our test objectives with the lab equipment we've been looking at. The Fineness Test relies directly on that 90-micron sieve. Consistency and setting time, both of those belong to the Vicat apparatus. The Soundness Test requires the Le Chatelier apparatus. And for compressive strength, we need that huge, heavy-duty compression testing machine. Finally, let's do a rapid-fire review of the critical numbers we've gathered on today's tour. Standard cube size for testing strength, 70.6 millimeters. The minimum initial setting time for workability, 30 minutes. The maximum final setting time for complete hardening, 600 minutes. And the specific gravity of ordinary Portland cement, 3.15. Honestly, if you remember these specific facts, you are going to effortlessly breeze right through those state examination questions. And that brings us to the end of our explainer today. We've walked through the lab, seen the high-precision tools, the heavy machinery, and the exacting numbers required to turn raw cement into the unbreakable foundation of our modern world. So I want to leave you with this final thought. Which of these critical testing parameters will you master first to ensure structural perfection? Thank you so much for joining me on this lab tour. Keep reviewing these concepts, and as always, keep striving for engineering excellence.